Hello and welcome to the following revision session for AQA A-Level Physics Paper 2. So in today's revision session, what we're going to be doing is we're going to be looking at how to answer examination questions on A-Level Physics Paper 2. So if we've been successful and learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. Now, to carry out this revision session successfully, I would suggest you divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in the left hand side write down your working out or answers to the question in the revision session. When you do this, make sure you write your answers in full sentences and show your full working out on calculations, whilst on the right hand side write down any piece of information you find useful or any hints and tips on answering questions gained from this revision session. Then after the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising your A-Level Physics? Well, the first step to carry out revision for A-Level Physics is to learn the key facts. So use your revision guides, class workbooks, student prep notes and the textbook to learn the key ideas of the course, which may include you making mind maps or writing out notes yourself. The second step is to test yourself. So use e-learning platforms such as Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Whilst the third step is practicing examination style questions. So use examination prep books, homework books, supervised study books, additional workbooks to answer examination questions and then mark your own work, and you may wish to download your own examination past papers to do this. So these three steps of learn the key facts, then testing yourself, then practicing examination questions are how I would revise your A-Level Physics. Now in this revision session we're going to focus on step 3, practicing examination style questions, and the first topic we're going to focus on is thermal physics. So look at the following question. Explain what is meant by specific latent heat of fusion. Then figure 1 shows how the temperature of the water is maintained in a hot tub. The hot tub system has a volume of 4.5 meters cubed and is filled with water at a temperature of 28 degrees Celsius. The heater transfers thermal energy to the water at a rate of 2.7 kilowatts whilst the pump circulates the water. Assume that no energy is transferred to the surroundings, then calculate the rise in water temperature that the heater could produce in 1 hour. So, pause the video now, then unpause the video when you want to go through the answers. So, the first thing we need to look at is what's the definition of specific latent heat of fusion. Now again, there's two key ideas to this. Firstly, it's the idea of specific, what's meant by that, and secondly, it's this idea of fusion. So, what's our definition of fusion going to be? So firstly, the specific latent heat of fusion is the energy to change 1 kilogram or per unit mass from the solid state to the liquid state. Now that's including the idea of specific, which is the idea of 1 kilogram or per unit mass, because that is what specific means, but also the idea of fusion, which is the idea of solid to liquid or liquid to solid, so melting or fusing. And then finally, the second mark is because it's the latent heat, that means that there's no change in temperature, because as we're aware, when we're changing the kinetic state, which is the change in temperature, you can't change the potential energy store, which is the change in state. So as a result, if we're changing our potential energy store, we can't be changing our temperature, because that's a different store. The second question, what do we have to do? Well, we're looking at the rise in water temperature. So we know that if we're changing temperature, we're changing the kinetic energy store. So the equation to work this out is delta Q is equal to mc delta theta. So therefore, we can work out what's going on, but we also were given the power. Now, power is energy over time, or delta Q over delta T, so we can therefore equate the two, because we know that there's no energy lost to the surroundings, so therefore all of the energy being transferred in by the heater is being used to raise the temperature. So we can say delta Q over delta T is equal to mc delta theta divided by delta T. So at that point we can then work things through and rearrange it and work through what delta theta is. And then we can also work out mass in our question, because we've been given the density and the volume, so therefore we know mass is density times by volume, work it all through, and we get an answer for delta theta to equal 0.51 Kelvin. Now again, you check to yourself, Is this going to be a sensible answer? And yes it is, because we're heating up an entire hot tub, so therefore it's only going to change by about half a degree or so. Right, next question. Figure 1 shows a perfectly insulated cylinder containing 0.050 kilograms of liquid nitrogen at a temperature of 70 Kelvin. A heater transfers energy at a constant rate of 12 watts to the nitrogen. A piston maintains the pressure at 1.0 times 10 to the 5 pascals during the heating process. The nitrogen is heated from 70 Kelvin and is completely turned into a gas after 890 seconds. Calculate the specific heat capacity of liquid nitrogen and give an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through the answers. So let's go through our answer to this question. So what do we know? Well, firstly, we can work out the energy which is being provided into the gas when it's being heated. By doing the equation again, energy is equal to power times by time. Remember, if you're given a power, you can then work out what its energy is going to be by doing energy is equal to power times by time. So the first thing we do is we do 12 times by 890, and that gives our energy going in to be 10,680 joules. Then we know to heat the energy to evaporate the nitrogen at its boiling point is equal to ml. So we therefore know that we can say that E equals ml. So we know that 0.05, which is going to be our mass, times by 2 times 10 to the 5, which is our specific latent heat, is equal to 10,000. So we know that the total energy supplied is 10,680. We then know that the energy needed to change the state is 10,000. So therefore the energy needed to change the temperature, okay, to change the kinetic energy store, is going to be that 10,680 minus 10,000, so it's 680. There's our energy going into changing the kinetic energy store. So therefore Q equals mc delta theta. So we can use that to work out C by doing C is equal to Q over m times by delta theta. We can then pop in the numbers and work it through. Remember, it's delta theta, so we're going to have to work out the change in temperature. So it's 77 minus 70, and we get our answer to be 1.9 times 10 to the 3. Again, look at that. Does that look a sensible value? And it does. Now again, you've then got to know your units for specific heat capacity. So you know that specific heat capacity is the energy over the mass times by the change in temperature. So it's joules over kilograms Kelvin. So as a result, or joules per kilogram degree Celsius, because we're using our energy over mass times by change in temperature. Next question. What is meant by the internal energy of a gas? An absolute zero of temperature can be interpreted in terms of the ideal gas laws or the kinetic energy of particles in an ideal gas. Describe these two interpretations of absolute zero of temperature. So pause the video now, then unpause the video when you want to go through your answers. So it's very important you learn your definitions of internal energy of a substance, especially a gas. So remember, our internal energy tends to be the kinetic energy store plus the potential energy store. So we should know that it's the sum or the total of the kinetic energies and the potential energies of all of the particles in the substance. It's important you status of all the particles in the substance, and don't just generalize it in terms of the stores. You've got to say it in terms of the particles that make up the stores. Now again, for the kinetic energy of the gas, it's going to have to be the gas molecules that make it up. Now, how can you work out the absolute zero of the temperature? Now, this is an important idea to understand in terms of what absolute zero is. Now, according to the gas laws, we know that it's the temperature at which the volume or the pressure of a gas extrapolates to zero, because we know that if PV is equal to nRT, which is the equation for an ideal gas, we know that if T is equal to zero, therefore P in V must also equal zero, because if one side of the equation equals zero, so does the other. Now you can also work it out, because when you plot volume against temperature, it's where it actually crosses the temperature axis. That's what absolute zero will be, because that is where you will get no pressure or no volume. And the second definition is in terms of the internal energy. So to think about it, you would describe the absolute zero temperature to when the kinetic energy store is zero. So as a result, it would mean that the particles would stop moving, they'd have no temperature, that have no movement. So therefore the internal energy at that point is purely the potential energy store. So you can define it in terms of that. So you can also say the absolute temperature, or the absolute zero temperature of a material is when the internal energy is purely potential energy and not kinetic. Let's have a look at the next question. Which statement explains why energy is needed to melt ice at 0 degrees Celsius to water at 0 degrees Celsius? Then figure 5 shows an experiment to measure the specific heat capacity of ice. A student adds ice at a temperature of minus 25 degrees Celsius to water. The water is stirred continuously. Ice is added slowly until all the ice has melted and the temperature of the water decreases to 0 degrees Celsius. The mass of ice added during the experiment is 0.047 kilograms. Calculate the energy required to melt the ice at a temperature of 0 degrees Celsius. The specific latent heat of fusion of water is 3.3 times 10 to the 5 joules per kilogram. So pause the video now, then unpause the video when you want to go through the answer. Right, so what do we know about this? Well, when we are changing state, it knows that we're altering the bonds of the substance. But it's important to note that when you're going from a solid to a liquid, you're only breaking some of the intermolecular bonds. Because you're not breaking all of the intermolecular bonds, because going from a solid to a liquid, you're not completely separating all the particles from each other, only a few of them. So you're only breaking a few of the bonds, not all of the bonds when you're going from solid to liquid. Now the next question, we're going to have to look at how you can work out the energy required to melt the ice. Now if you're melting ice, that means you're changing the state, which means that we're using the specific latent heat of fusion equation. So we'll be using E equals ml. Now we know what our mass is, it's 0.047 kilograms. We know what our specific latent heat of fusion is, 3.3 times 10 to the 5. So we get our answer of 1.6 times 10 to the 4 joules. Next question. The water loses 1.8 times 10 to the 4 joules of energy to ice during the experiment. Calculate the energy given to the ice to raise its temperature to 0 degrees Celsius. Assume that no energy is transferred to or from the surroundings in the beaker. Then calculate the specific heat capacity of the ice and state an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answers. Right, so how do you answer this question? Well, it's important to note that the energy in from the water is equal to the energy supplied to melt it, which is the change in the potential energy store, plus the energy needed to raise the temperature, the kinetic energy store. So we can say that the total energy, which is 1.8 times 10 to the 4, is equal to the energy needed to change the state, which we just worked out to be 1.6 times 10 to the 4, plus this value of x, the energy needed to change the temperature, to change the kinetic energy store. So therefore it's going to be 1.8 times 10 to the 4 minus 1.6 times 10 to the 4, which is 0.2 times 10 to the 4, or 2 times 10 to the 3 in standard form. So now if we're trying to calculate the specific heat capacity of the water, we know that the equation is delta Q is equal to mc delta theta. Now as a result, we just worked out in the previous question what delta Q is, the change in the kinetic energy store, to be 2 times 10 to the 3. So therefore C is equal to this 2 times 10 to the 3 over m times by delta theta, which is going to be 0.047 from the previous part of the question, times by the 25, because that is the change in the temperature. So you get your answer to be 2 times 10 to the 3 over this value of 0.047 times by 25, so you get your answer to be 1.7 times 10 to the 3, and again learn your units of specific heat capacity. It's joules per kilogram Kelvin or joules per kilogram degree Celsius, because it's energy per mass times by change in temperature. The next set of questions we're going to look at now are to do with electrical fields. So figure 7 shows the charged oil drop stationary in air in an electrical field between two parallel plates. The potential difference between the plates is V. Draw and label arrows on figure 7 to represent the forces acting on the oil drop, and the potential difference between the plates is now reversed so that the oil drop is attracted towards the lower plate. Explain why the initial acceleration of the oil drop is approximately 20 meters per second squared, and then describe and explain the motion of the oil drop after the potential difference between the plates is reversed. So pause the video now, then unpause the video when you want to go through your answers. So, what do we know in this particular situation? If our oil drop is stationary in midair, it tells you that the force going upwards and the force going downwards are going to equal each other. Now, the force going downwards is going to be gravity, mg, while the weight. So that whilst going upwards is going to be the electrical force, which is going to be vq over d. So equal each other out. Now, you think to yourself that at this point, that because w is equal to the electrical force, and we know that w, which is going to be the acceleration, would link to the acceleration due to gravity, which is 9.8. So therefore, if we know that the acceleration due to the weight is 9.8, well, therefore the acceleration due to the electrical field is also going to be 9.8. Now, if you reverse the potential difference, that means you reverse the direction of the electrical force, so reverse the direction of the acceleration caused by the electrical force, so therefore it's 9.8 times by 2, which is approximately going to equal 20, or it's going to be equal 19.62. Then describe and explain the motion of the oil drop after the potential difference between the plates is reversed. So if there's a resultant force downwards, this tells us that the force is acting downwards, so the acceleration is going to act downwards. But as the object moves downwards, the air resistance opposing this thrust force due to the gravitational force and the electrical force is going to increase and increase with speed until eventually they reach terminal velocity. Next, we're now going to look at some questions to do with capacitance. So look at the following question. When a 470 microfarad capacitor is discharged through a fixed resistor R, the PD across it decreases by 80% in 45 seconds. Calculate the time constant of the capacitor resistor circuit, then determine the resistance of R. So pause the video now, then unpause the video when you want to go through your answers. Right, so how would you answer this question? Now, there's a number of ways in which you can do this, but the easiest way in this instance is to use the equation of discharge for a capacitor. So you would say V is equal to V0 e to the minus t over RC. Now you can work it through. That says that the potential difference, which is V, decreases by 80%. So if we say V0, which is the starting potential difference in a discharging capacitor, is 100% or 1, we can therefore say that V is going to be 0.2. V0, because it's the 20% of the original value. So we can now change V to be 0.2 V0. So at that point we can then take V0 to the other side, so it'll be 0.2 V0 over V0, and therefore the V0s cancel through, so you get 0.2 is equal to e to the minus t over RC. Now t is equal to 45, so you then take the natural log of both sides, as that removes this e term, so it goes log 0.2 is equal to minus 45 over RC, because a log e means that it removes the e and the natural log, and then the power value just becomes a normal term in the equation. So therefore we can say log 0.2, which is also log 5, is therefore going to equal 45 over RC. Sorry, I should say log 0.2 is equal to minus log 5, so therefore it can remove the minus sign. So therefore we can say log 5 is equal to 45 over RC. We can work it through and we get 28 seconds, which again looks an approximately correct answer. Now determine the resistance of R. Well, we've already been told in the question that the capacitance of the capacitor is 470 microfarads, so 470 times 10 to the minus 6. So we know that T, the time constant, is equal to RC, so therefore R is equal to the time constant over C, so it's that value you worked out previously, 28, divided by 470 times 10 to the minus 6. Remember, we've converted our micro into times 10 to the minus 6, so we get 5.96 times 10 to the 4, or 60 kilo ohms. Next question. Figure 4 shows how the current varies with time as the capacitor is discharged through a 150 ohm resistor. Explain how the initial charge on the capacitor could be determined from a graph of current against time, and the same capacitor is charged to the same initial potential difference and then discharged through a 300 kilo ohm resistor. Sketch a second graph on the same axis above to show how the current varies with time in this case. So pause the video now, then unpause the video when you want to go through your answer. So, what do we know about how we could work out the initial charge? Well, we know that charge is going to be equal to I times by t. Now, it's important to note that in a graph, if you do the y divided by the x, you would get the gradient. If you did y times by the x in terms of the axes, you would get the area. Now we know that charge is equal to current times time, so we're doing y-axis times by x-axis, which indicates to us it will be the area under the graph, the area between the line and the axis. Now the next question is, the same capacitor is charged and then is discharged to that 300 kilo ohm resistor, sketch on a second graph. So you notice that the line would now start at about half of the original initial current. You know this because the resistance has doubled, so therefore current and resistance are inversely proportional. So if the resistance is doubled, the current halves, so the initial value is half. Now the second thing to note is you've got a slower discharge and exponential graph because there's a smaller value, so as a result it will discharge exponentially slower, but the correct line will intersect at the original curve, i.e. it meets at the end, because they'll always finish at the same value. The capacitor will discharge to the same final value. It might take longer to do so, but it will do so to that final value. Let's now have a look at some questions on magnetic fields. So let's look at this first question on magnetic fields. Figure 3 shows an arrangement for investigating electromagnetic induction. When the switch is closed, there's a current in the coil in circuit X. The current is in a clockwise direction as viewed from position P. Circuit Y is viewed from position P. Explain how Lenz's law predicts the direction of the induced current when the switch is open and again when it is closed. So pause the video now, then unpause the video when you want to go through your answer. So, what do we know about Lenz's law? It's very important you know the definition of Lenz's law. Now, Lenz's law is such that the induced current is produced in a direction that opposes the change that produced it. That is Lenz's law, and you should always state it when I ask you to discuss Lenz's law. So, if you think about it, when you switch on the circuit, that then produces a change in the magnetic flux linkage, and remember, it's a change in magnetic flux linkage that produces an induced EMF, which in a circuit will produce a current. Now it's a positive change, so the current will oppose the direction, or being anti-clockwise, to create an opposing flux to the change that caused it. Now when you switch off the flux, when you turn off the circuit, you still have a change in magnetic flux linkage. It's just now a negative change. It's going down, but that change in flux linkage will produce an induced EMF, which leads to a current in the circuit. Now it will actually cause the current to travel clockwise to create a flux to oppose the decrease. So what will actually happen is that it will actually cause the current in the circuit to increase slightly when that change takes place. Next question. A cyclotron has two deep-shaped regions where the magnetic flux density is constant. The D-shaped regions are separated by a small gap. An alternating electrical field between the D-shaped regions accelerates charged particles. The magnetic field causes the charged particles to follow a circular path. Figure 4 shows the path followed by a proton that starts from O. Now explain why it's not possible for the magnetic field to alter the speed of a proton and whilst there's one in one of the D-shaped regions. And then derive an expression to show that the time taken by a proton to travel around one semicircular path is independent of the radius of the path. Then finally, the maximum radius of the path followed by the proton is 0.55 meters and the magnetic flux density of the uniform field is 0.44 teslas. Ignore any relativistic effect and calculate the maximum speed of a proton when it leaves the cyclotron. So pause the video now, then unpause the video when you want to go through your answer. Right, so it's the first one. We've got to be aware of the direction of the magnetic field in this situation. Now in the question they'll always give you a hint, and the hint is it's very clear that the magnetic field is going into the page. Now you should be aware that a force will only cause a particle or an object to change speed if it's acting in the direction of the actual motion, if there's a component of that force in the direction of the motion. Now it hasn't got any component in the direction of the motion because the magnetic field is acting perpendicular to the direction of motion. It's acting as a centripetal force. Next one, derive the expression. So what you need to do is work out the expression for the time taken of the proton to travel around one semicircular path and show that the radius is not in the equation. So what you'd say is you'd look at what's going on, and our magnetic force is acting as the centripetal force in the equation. So you would therefore say BQV is equal to mv squared over r. The magnetic force is equal to the centripetal force. But we also know that the time taken to travel in a semicircle is distance over speed, which which is going to be pi r, which is the distance of the half circumference, the circumference of the semicircle, divided by the velocity. So what we then do is we then say that distance, which is equal to 2 pi r, okay, if we're going to do the full time, could be equal to v, and do it like that as well. But let's just stick with a semicircle. So we can say that t is equal to pi r over v. And then we can work out what v is from that starting equation. So what we can then do is pop that into the equation and then say that pi m over bq. So as a result, that term of r has cancelled through. So we can work it out, and it's cancelled through because our pi r over v, when we're subbed in the equation for that particular value of r, works through, cancels it all through, and therefore you can say that r is not in the equation. So as a result, that's our proof. Now again, the next thing to note is when you have something where the magnetic force is acting as the centripetal force in the situation, you would say that mv squared over r is therefore equal to bqv, which is what we're saying is that the centripetal force is the magnetic force. So the centripetal force mv squared over r is equal to the magnetic force bqv. We then rearrange it and therefore make the work out the equation. So we know that r is equal to mv over bq. So therefore v is going to equal bqr over m. So therefore we can pop in our values, work it through, and we get 2.3 times 10 to the 7, which again, if we look at the values we estimated, looks an appropriate value. Let's have a look at the next question. State Lenz's law, and then Lenz's law can be demonstrated using a bar magnet and a coil of wire connected to a sensitive ammeter as shown. The bar magnet is moved towards the coil and is then brought to a halt. State how the reading on the ammeter changes during this process. Then during the demonstration, an induced current is detected by the ammeter. The induced current is in the direction E to F. Explain how this demonstrates Lenz's law. So pause the video now, then unpause the video when you want to go through the answers. Right, once again, it's very, very important you learn your definition of Lenz's law. So what's our definition of Lenz's law? That the direction of the induced EMF is such to oppose the change that caused it, that produced it. Now remember, Lenz's law indicates the direction of the induced EMF, whilst Faraday's law indicates the magnitude of the induced EMF. Next question, what will happen? So what will happen is that you will have a current flowing and then it will become zero. Why will you get a current flowing? Well, you get a current flowing because you get a change in magnetic flux linkage because the bar magnet is moving through the coil. But then when it's brought to a halt, you will still have a flux linkage because the magnet will be inside the coil, but you wouldn't have a change in flux linkage, which is what you need for an induced EMF, which then produces the current. So as a result, what would you then happen? It would have a flow and then it would stop. Next one, how does this particular demonstration show Lenz's law? Well, it's a point that there's a therefore, if the induced current is in the direction of E to F, well, this tells us that there must be a north pole on the right hand side of the coil. So therefore, we're opposing the motion of the bar magnet. We are repelling the motion that is causing it to be produced. So what's happening is it's trying to maintain the magnetic field as the magnet approaches the coil, because otherwise, without this, the magnet would increase the magnetic field beside the coil. You can't produce energy, you can't gain energy, which is what the purpose of Lenz's law is there. It's to conserve energy in the situation. Next question. Figure 7 shows the arrangement for investigating induced EMF. As shown, the uniform vertical magnetic field is confined to the gap between the poles of the magnet. The plane of the square coil is horizontal and is made of conducting wire. The coil consists of a single turn and is attached by flexible wire to an oscilloscope. The oscilloscope gives a reading of 2.9 times 10 to the minus 4 volts when the coil is moved at a uniform speed from position G outside the field to position H inside the field, as shown in figure 8. Now calculate the time taken to move the coil from position G to position H. So once again, pause the video and then unpause the video when you want to go through your answer. Right. So what would you do here? So the first thing is the importance of how to work out the induced EMF in this situation. Now the most common equation to use is the induced EMF is equal to BLV, which again is an equation you've got to be aware of. Now you know that V, velocity, is equal to the displacement over the time. So therefore you can pop that time into the equation by saying EMF is equal to BL S over V. So therefore we can work it through and make S over T, and therefore we can make T the subject. We can then pop in our values, because if you look in the question, you've got lots of different values. You've got the induced EMF, you've got the length, which is the displacement. Obviously we'll convert that into meters, so we say it's 32 times 10 to the minus 3. We've got our value of B, we pop them all in there, and we get our answer to be 1.34 seconds, which again sounds like an appropriate answer, so is most likely going to be correct. Next question. The square coil is rotated through 360 degrees at a constant angular speed about the horizontal axis shown in figure 9. Calculate the angular speed of the coil when the maximum reading on the oscilloscope is 5.1 millivolts. So pause the video now, then unpause the video when you want to go through your answers. Right, so how would you answer this question? Well, you're looking at working out a value when you've got the maximum induced EMF. Now, as opposed to the previous question, which just worked out the induced EMF, not the maximum possible induced EMF, you've got to use the maximum induced EMF equation, which is equal to BAN omega sine omega t, which then simplifies for the maximum to be BAN omega. Now, it's important that you really know the difference in the equation. So EMF is equal to BLV, is just any EMF, whilst the maximum EMF is equal to BAN omega, and it's really important you know all those different equations for electromagnetic induction. Now we want to work out omega, the angular speed, so we rearrange the equation and we say EMF maximum is divided by BAN is equal to omega. So then pop our values in, making sure we pay close attention to the fact that in the question we have not been given the area, we've been given the length of one side, and because it is a square you can then just times the two numbers by each other or square them like they've shown on the mark scheme here. So we do 5.1 times 10 to the minus 3 divided by 0.38 times by 0.032 squared, and work it out to be 13.1 radians per second. Right, we're now going to look at some questions on nuclear physics. So let's look at the first question. An ancient sealed flask contains a liquid assumed to be water. An archaeologist asked the scientist to determine the volume of a liquid in the flask without opening the flask. The scientist decides to use a radioactive isotope of sodium that decays with a half-life of 14.8 hours. She first mixes a compound that contains 3.0 times 10 to the minus 10 grams of sodium-24 with 1,500 centimeters cubed of water. She then injects 15 centimeters cubed of the solution into the flask through the seal. Show that initially about 7.5 times 10 to the 10 atoms of sodium are injected into the flask. Then show that the initial activity of the solution that is injected into the flask is about 1 times 10 to the 6 becquerels. So pause the video now, then unpause the video when you want to go through the answer. Right, so how can we work out that there were initially 7.5 times 10 to the 10 atoms of sodium injected into the flask? Well, it's the idea of how many atoms are going to be in 1 gram in this instance of your sodium, which links into a little bit of chemistry. So the first thing we need to note is we've been given the mass of the sodium in grams, so we can turn this into the number of moles of sodium that we've got. So we can turn this into the moles of sodium by doing the mass in grams divided by the mR of sodium, which you're told in the question is 24. So the first thing we can say is that we do 3.0 times 10 to the minus 10, then divided by 24. That tells us how many moles of sodium that we've got. The next thing is we know that in 1 mole there is 6.02 times 10 to the 23 atoms. We know because of Avogadro's constant, so we multiply the number of moles by Avogadro's constant, 6.02 times 10 to the 23, to get our answer of 7.52 times 10 to the 10. Now the next question, show your initial activity. Now it's important that they've given you the half-life, because if you're given the half-life you can work out the decay constant in this situation very easily, because you know that the decay constant is log 2 over the half-life, which is 0.69, that's log 2, divided by 14.8, so you get 1.35 times 10 to the minus 5 seconds when you've converted your hours into seconds. So therefore we now know what our decay constant is, and then we know that activity is going to equal the decay constant times by the activity that you're given. So by the number of atoms, sorry, because we know A is equal to lambda n. So we, in the previous question, worked out the number of atoms, which was 7.52 times 10 to the 10. We then multiply by the decay constant we've worked out, and we get 9.75 times 10 to the 5 becquerels. Now, it's very important you know which equations to use and how you can link in the decay constant to the half-life. Next question. The core of a thermal nuclear reactor contains a number of components that are exposed to moving neutrons. State what happens to a neutron that's instant to a moderator. State what happens to a neutron that's instant on the control rod. Then a slow moving neutron is in collision with the nucleus of an atom of fuel which causes fission. Describe what happens in the process. So pause the video now, then unpause the video when you want to go through your answers. Right, so it's important to note that for a moderator, the moderator will slow down those fast-moving neutrons, and it does this by having the neutron undergo an elastic collision, so it bounces off with less kinetic energy, okay, with the moderator. Remember, it's always important the idea to the moderator collides with those fast-moving neutrons, so they will move with less kinetic energy. Now, what will happen when it's instant on a control rod? Well, the control rod absorbs certain neutrons, so they don't all fission and further on. So it controls that chain reaction. So as a result, the neutrons are absorbed by the control rod, a fact you've got to remember. Now, what happens when it collides with uranium-235? So the neutron is absorbed by uranium-235, so uranium-236 is formed. So therefore this nucleus, not atom, but this nucleus, it's important to always state it's the nucleus that absorbs the neutron, not the atom, is then split into two smaller nuclei, which we'll call daughter nuclei, and will release several fast-moving neutrons. Remember, there's always more than one neutron. The average number of neutrons released in the fission process for uranium-235 is 2.3, which tells us there's either 2 neutrons or 3 neutrons released. Now again, remember, this is what happens with uranium-235. With uranium-238, the neutron is absorbed, but it does not cause further fission. Next question. The age of the moon has been estimated from rock samples containing rubidium and strontium brought back from the moon landings. Rubidium decays into strontium with a radioactive decay constant of 1.42 times 10 to the minus 11 years to the minus 1. Calculated in years the half-life of rubidium. A sample of moon rock contains 1.23 milligrams of rubidium. Calculate the mass in grams of rubidium that the rock sample contained when it was formed 4.47 times 10 to the 9 years ago. Then calculate the activity of a sample of rubidium of mass 1.23 milligrams, given an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so once again, you've got to see the link between the decay constant and the half-life, a very important skill to recognize. So half-life is equal to log 2, or 0.69, divided by the decay constant. So the time constant is 0.69 over 1.42 times 10 to the minus 11. Note you don't need to change the units of the decay constant because it wants the half-life in years. So you get an answer of 4.9 times 10 to the 10 years. Now, next question is calculating the mass. So we've got to use our decay constant equation. So we'll notice that we'll use our equation of m is equal to m0 e to the minus lambda t, where m is that mass at that particular point in time, m0 is the initial mass, and minus lambda is the decay constant. Remember, it's a minus because it's decreasing in size, the mass because it's decaying, and then times by the time which you're measuring. So therefore we can say m over m0 is equal to e to the minus lambda t. But also what we've done here is we need to actually work out m. So what we can actually do is flip it over and say m0 over m is equal to e to the plus lambda t. You'll notice we can do that because we've just flipped over the equation, and when you flip over the equation with an exponential of a negative, it becomes a positive. We've done this because we wanted to work out the bottom term on that equation, so it makes it a lot easier to do. So we can then rearrange that and say m0 is equal to m times by e to the positive lambda t. That's a good trick to do about how you can flip over those values when you just change the sign of the exponential term. So therefore we can work out lambda t. So we know lambda to be 1.42 times 10 to the minus 11. We then multiply that by the number of years, which is 4.47 times 10 to the 9. Remember, we don't have to change units because they're both in years. So therefore we can work out what m0 is going to be by saying it's a value of m, which we know to be 1.23 times 10 to the minus 3, times by e to the power of 1.42 times 10 to the minus 11 times by 4.47 times 10 to the 9, which comes out to be 1.31 times 10 to the minus 3 grams. Now again, it's important to note that we keep the correct number of significant figures. So if there's 3 significant figures given for the decay constant, there's 3 significant figures given for the mass, you've got to give your answer 3 significant figures. And note we were given milligrams in the question, but we needed the answer in grams, so we converted from milligrams to grams, so it's 10 to the minus 3. Next, calculate the activity of the sample of rubidium of mass 1.23 milligrams. So what you would then do is you can also use the equation A is equal to lambda n. Because we know what lambda is, we need to work out A, the activity. So as a result, we can work it out with the equation A is equal to lambda n. But we need to work out what n is. So we know n, which is the number of nuclei, is going to be equal to the mass divided by the MR. So we work it through by doing 1.23 times 10 to the minus 6, which is the mass, dividing it by 86 times by 1.661 times 10 to the minus 27. So sorry, what I meant by that is not the MR, rather it is the conversion from the atomic units into just kilograms. So you therefore work it through to be 8.5 times 10 to the 18, because what we've done is we've worked out what the mass of the total was. We've then worked out what the mass of one of the atoms were, so we can work out how many atoms we had. So the mass of the total was 1.23 times 10 to the minus 6, whilst the mass of one of the atoms itself was 87, well, nuclei I should say, really, 87 times by 1.661 times 10 to the minus 27. You know this from the question because you're told that strontium has a overall mass of 87 nucleons. So you convert that 87 nucleons into kilograms. So you get N is equal to 8.5 times 10 to the 18. A is equal to lambda n, so we know lambda to be 1.42 times 10 to the minus 11, but we need to now be in seconds because we're going to get our answer in becquerels, which is in seconds because it's an SI unit. So we convert our decay constant into seconds by dividing by 365 times by 24 times by 60 times by 60, the number of seconds in a year. So we get our decay constant to be 4.50 times 10 to the minus 19. So A is equal to 4.5 times 10 to the minus 19 times by 8.51 times 10 to the 18, which is equal to 3.8 becquerels. Next question. Table 1 shows the nucleon number A and the nuclear radii R for 3 nuclides. It suggests that A is equal to R cubed over K, where K is the constant. Use the data in Table 1 to determine a reliable value for K. Determine the percentage uncertainty of the value of K you found in 2.1. And the mass of a nucleon is 1.67 times 10 to the minus 27. Show that the data in Table 1 supports the idea that nuclear material has a constant density. Right, so pause the video now, then unpause the video when you want to go through the answer. So what you'd do for this first question is you'd rearrange it and make K the subject. You say K is equal to R cubed over A, then you do all 3 rows. You've got a value of R, you've got a value of A, work it through and get your answer out. Now you should really, because there are 3 values there, do all 3, then find the mean of the answers. Now when you've got your 3 values, you can work out your percentage uncertainty by doing your absolute uncertainty divided by the average value, which you worked out in the previous question, times by 100. Now to work out the absolute uncertainty, well, you've done it 3 times, so in essence you've got 3 repeats. So when you've got repeated readings, you can work out an absolute uncertainty by doing range divided by 2. So what you would therefore do is you find the range of the values, you divide it by 2, that's your absolute uncertainty, you then divide it by the mean value, which you calculated previously, and multiply it by 100, that's your percentage uncertainty. Now show that the data in the table 1 supports the idea that the nuclear material has a constant density. So what you then do is you would try to work out the densities by doing M is equal to 1.67 times 10 to the minus 27 times by A, and V is equal to 4 over 3 pi R cubed, and therefore density is therefore going to be equal to A over V. So you'd work out the M for each one by multiplying your value of A by 1.67 times 10 to the minus 27. You'd then work out your volume by doing 4 over 3 times by pi times by R cubed. You can work out your value and show that they are constant. Now also it's important that if they are constant, you give a conclusion to state that. Don't just show your calculations and then give a statement. Next question. This question is about the Rutherford scattering experiment. The nuclear radius cannot be bigger than the distance of closest approach of an alpha particle. Complete figure 2 to show the paths followed by each alpha particle. Then the nuclear radii can be found using the diffraction of high energy electrons. Sketch on the axis below a graph showing the variation of electron intensity with diffraction angle. Label angle theta using the calculation of the nuclear radius. So pause the video now, then unpause the video when you want to go through your answer. So, first thing you've got to understand is the top path is very, very far away from the alpha particle. Now, it's the electromagnetic interaction that will cause a repulsion between the positively charged alpha particle and the positively charged nucleus. So that decreases with distance, so it's too far away to cause a deflection, so it will go straight through like nothing's happened. The middle path will be reflected along its own path, and the deviation will be greater than that of the top path, and the distance of closest approach is on the middle one, because that's the one that's going to be hitting dead on. So as a result, you can see those different values. Next one, what would it look like? Again, this is a memorization you've got to know. So it looks something similar to this, with the first non-zero minimum dip there labeled theta, because that's our first angle diffraction. Again, you've just got to memorize that shape of the graph. Next question. A thermonuclear reactor uses a moderator to lower the kinetic energy of fast-moving neutrons. Explain why the kinetic energy of neutrons must be reduced in a thermonuclear reactor, and the result of a collision with an atom of particular moderator, a neutron loses 63% of its kinetic energy. A neutron has an initial kinetic energy of 2.0 MeV. Calculate the kinetic energy of the neutron after 5 collisions. So pause the video now, then unpause the video when you want to go through your answer. Right, so why do we reduce the kinetic energy in a thermonuclear reactor? Because that increases the probability of chance of further fission. Because if the neutron is slowed down, it will be more likely to be absorbed by the uranium-235 and cause further fusion. That is the job of the moderator. Now, how can you work out how much the energy has gone down by after 5 collisions? So the way you can do it is that if it loses 63% of energy every single time, therefore it must be left with 0.37 or 37% of the energy. So what you've then got to do is, because it's happening 5 times, you would do 1 minus 0.63 or 0.37, and then you would actually multiply by the power of 5, because to work it through by this 5 collisions, and you're working basically 37% each time, you would do that to the 5th power, because there's 5 collisions. So you do 0.37 to the power of 5 times by that initial energy. Now it's important that, because we're going to be working in EV here to get our final answer, you've got to convert your MeV into EV. So it's not going to be 2 MeV, it's going to be 2 times 10 to the 6 EV, because M means big M, mega means million, or 10 to the 6. So you get your answer out to be 1.4 times 10 to the 4 EV, which you could then convert into joules if you wanted to, by times them by 1.6 times 10 to the minus 19 joules. Let's have a look at the next question. State and explain the results of the scattering experiment, including the main observations, the significance of each observation, and then explain how the observations place an upper limit on the nuclear radius. So pause the video now, then unpause the video when you want to go through your answer. Right, so in these types of questions, you've got to really answer each point. Now, it's actually quite useful to look at the descriptor levels on how you get 5 to 6 marks. So you'll have to give an idea of covering all 3 bullet points and explain these clearly. And not just state key facts, but also explain your answers clearly, and then also talk about in another approach to find the upper limit to the radius. So talking about as a whole, taking it on further, developing it. So not just giving some standard answers, rather developing those answers, but clearly answering all 3 bullet points. So what do we know about? Firstly, in Rutherford scattering, most alpha particles pass straight through, which suggests that the atom is mostly empty space. Some alpha particles are backscattered or scattered by more than 90 degrees, which suggests that they have interacted with something much more massive than themselves due to momentum. So if they're reflecting backwards, it must be that they're the smaller object. And they'd be repelled by a concentrated positive charge. So they've had the Coulomb repulsion. They've been repelled by the electrical potential energy between that particle and the nucleus. So that suggests that there must be a really, really strong, very, very dense positive charge in the center of your atom. Then you'd also then consider the proportion of the alphas passing straight through compared to how many reflect backwards. So it's the idea that if 1 in 10,000 alpha particles is backscattering, then this positive charge must be about 10,000 times smaller than the actual atom itself. Now, because we've got the appreciation that when these alpha particles are backscattering, they're not actually colliding with the positively charged nucleus, rather they're being repelled. So they actually don't hit the actual atom, which is why our value for the radius is an upper limit, because we're not actually measuring the size of the atomic radius, rather we're measuring the distance of closest approach, how close the positive alpha particle can get before it is repelled by that positively charged nucleus. Now, it's important to note that the kinetic energy of the alpha particle is then changed into electrical potential energy due to that repulsion, so that will therefore allow you to work out the upper limit of the nucleus. Now, the idea that backscattering wouldn't occur if you could actually get the alpha particle really close is an important one, because the strong nuclear interaction would take over. If that alpha particle got very close to the nucleus, it would capture it and it wouldn't actually reflect backwards. So in Rutherford's scattering experiment, you can't really ever find the size of the nuclear radius, because you can't actually get close enough and have your alpha particle return to you. So let's look at a quick checklist of how to get your marks here. Most alpha particles go straight through because the atom is mostly empty space. A very small amount of alphas are backscattered because there's a large positively charged nucleus in the center of our atom, and the method to suggest to find R is the idea of the straight on beam, but it's going to be a backscattering, but that's only the upper limit because of the idea of the kinetic energy alpha turning into the electrical potential energy and not actually touching the surface of the nucleus, because if it did, the strong nuclear force would capture the alpha particle and not make it reflect backwards to be measured. So that brings us to the end of this revision session. I hope if you've been successful and learned in today's revision session, you can answer A-level physics examination style questions, assess your understanding on A-level physics, and then finally understand what topics you need to improve upon for A-level physics. So thank you very much for watching this revision session, and as always, have a lovely day.